everyone, my name is Ray Gong. I'm a PhD student from Griffith University, Australia, and I'm very excited to talk about our paper called Not All Edges Are Equally Robust, Evaluating the Robustness of Ranking-Based Federated Learning. And this work is a joint work from Griffith University, University of Technology, Sydney, and Deakin University. So to begin with, I will have a brief background introduction of our work. So our work is based on the federated learning and its security issues. As we know that the federated learning is a decentralized approach to machine learning that enables multiple clients to collaboratively train a model while keeping their data locally stored. And this approach can effectively mitigate the data silo issues and enable the training of machine learning models on diverse datasets. However, this decentralized nature of FL makes it susceptible to various client-side polling attacks, and it hinders FL's development in real-world applications. So, identify this issue for this work, we are focused on the security perspective of the FL framework, and we mainly aim to evaluating the robustness of existing FL frameworks and to identify some potential vulnerability to see if we can improve the robustness of the FL systems. So to begin with, we first conduct extensive literature review, and we identify the SOTA robust FL framework, which is called Federated ranking learning. And this Federated ranking learning is different from traditional FL training framework in two ways. So firstly, the FLL, it's utilize the edge ranking as a communication parameter between the client and the server instead of the model updates. And here the edge ranking, they indicate the importance of each neurons in the network, and it's in the format of the permutation of integers. And the second difference is that in the server side, it utilizes the majority voting to get the global ranking instead of the weight aggregations. And after get the global ranking, it further utilizes the lottery ticket hypothesis, which states that within the large neural network, there exists a sub-network that can achieve the same performance as the original full networks. So after get the ranking, it selects the top k edges to form the sub-network that can achieve the same performance as the original full networks. And this sub-network is finally used to form the global model. And then we try to analyze why this framework is robust against some client-side polling attacks. So there are two main reasons. So the first reason is that this ranking format, it narrows down the potential space for malicious update from the infinity range to the n factorial. And this format, they effectively bounding the source damage within the defined budget. And the second reason is that the server-side majority voting, they prevent the malicious client from making significantly modifications to the global model. As each client, they only have single vote, it's hard for a single client to change the consensus of other clients. So after analyze this framework, we will further want to evaluate how robust is this framework. So we conduct several experiments of SOTA attacks on this kind of framework, and we record the attack impact of each attacks under different malicious rate and different non-ID degrees. As we can see in this figure, the SOTA attacks, they all achieve very low attack impact on these frameworks. So after identifying this fact, our next question is there any vulnerabilities inside this framework, or is that framework are truly robust that can defend all any kind of polling attacks? So our work, so based on this question, we conduct our work. So here comes to the main contributions of our work. So we conduct the first systematic analysis of FRL's robustness, and we uncover a critical vulnerability in this framework. And based on the result of the analysis, we design and implement a new attack called VAM that can target and effectively manipulate the vulnerable edges. And we conduct extensive experiments across different network architectures and datasets, demonstrate that our VAM significantly outperforms SOTA attacks. And here's a threat model of our attack. For the attacker's objective, we consider the untargeted local model point attacks against the FRL's framework. And we assume that the authority controls up to M out of U clients in each iteration. We call the malicious client. And we consider update ignore setting where the authority does not have any information of other benign clients. And here is the overall framework of our attack method. We mainly include 3 stages. So in the first stage is called the vulnerable edge identification, where we theoretically prove that there exist some vulnerable edges in the network, and we derive upper and lower bound of how to find these vulnerable edges. And after identify this vulnerable edge, in the second stage, we formalize the optimization function to manipulate this vulnerable edge to make sure that the global model after attack and before attack, the global model of those vulnerable edges change the most. And after the optimization stage, in the final stage, we use our optimized parameter to generate our final malicious updates. And here's details of each steps. So for the first stage, vulnerable edge identification, to facilitate our analysis, we first formalize the FRL's method in a more tankable way. So specifically, we encode the edge ranking into a 2D metric to preserve the information that we need while avoiding some non-differentiable operations like sorting and get index operations. And based on our analysis, we aim to find the vulnerable edge in the networks. So our intuition here is that in the network, if the importance difference between one edge and the selection boundary is smaller than the maximum damage the authority can cause in one round, in that case, we call that edge a vulnerable edge. And based on this intuition, we prove the existence of the vulnerable edge in the network, and we derive upper and lower bound of how to find those vulnerable edges in each layer. And after the vulnerable edge identification, our next stage, we want to make sure that the global model's importance of those vulnerable edge after attack deviates significantly from their original values to maximize the authority's damage. So here we have our optimization function where we want to maximize the global model difference before attack and after attacks. But here the challenge is that the optimization function here is not continuous because here the edge ranking is in the discrete space, so we cannot solve that directly. So to address that challenge, here we utilize a gumbo synchron method to convert a discrete problem into a continuous problem. And by optimizing this continuous matrix, we can simultaneously update our discrete matrix and to optimize our objectives. And after solving this optimization function, in the final stage, we use our final optimized parameter to generate our malicious update. And here's come to the main experiment results of our attack. We compare our attack with 6 SOTA attacks under 7 different defenses. And as we can see in this figure, our attacks, they all outperforms others by large margin. And it achieves a 53% attack impact and is 3.7 times more impactful than other attacks. And also we conduct some ablation studies. For example, we calculate the attack impact of different percentage of malicious clients, and also the attack impact of different percentage of the non-ID degree of the dataset. And as we can see in the figure, our attacks, they all outperforms others by large margin. And here is some discussion and future works, because in this work we mainly investigate some untargeted point attacks against these systems. So in the future we want to investigate some targeted point attacks under this ranking-based FL to further evaluate the vulnerabilities of these systems. And also we want to propose some certified robustness evaluation method to further build a foundation of our attack. And also we want to evaluate design more robust FL framework with this like less knowledge in information sharing ideas. So that's all my presentation. Thank you everyone.